Let's take a look at how we can apply some of the simple harmonic formulae. So the first example we're going to look at is actually a mass hanging on to a spring. The mass is then given a slight tug downwards and release. Thereafter, the mass will bounce up and down about the equilibrium position, undergoing simple harmonic motions. How do we know that? So now let's take a look at the force equation. So mg is equal to Ke, and that is actually initially when the mass is actually at rest. So the extension is actually this portion here. So the extension is indicated here on the diagram. L is the initial length of the spring. The net force acting on the mass comprises two forces. One is the elastic spring force, the other is the weight mg. So in this case, you can see that mg is positive, as the convention we have chosen is downward is positive. For the elastic spring force is negative in value because it's actually directed upwards. So the elastic spring force in this case now is minus K bracket X plus E. And if we were to replace the mg with Ke, we will work out that Ma is equal to minus Kx. And from there, we're able to derive a relationship between the acceleration of the object undergoing simple harmonic motion with its displacement. And in this case, K over M will now be equal to omega squared. Now let's take a look at the oscillation of a pendulum. In this case, we'll assume that take a look at the pendulum swing. And in the example, we'll be assuming that the angle theta is small, hence there's insignificant change in the gravitational potential energy of the bob when it is actually undergoing swing, when it is actually undergoing simple harmonic motion. So let's take a look at the equation. When the bob is at a displacement x away from the equilibrium position, the net force acting on it is minus mg sine theta, as indicated in the force resolution of your weight mg by the two vectors as shown. As the weight is now resolved in two directions and indicated in the diagram, we can see that the mg sine theta is the force that is actually directed towards the equilibrium position. So the net force F equal to ma is equal to minus mg sine theta. So from there, the m and m cancel away. We will get A equal to minus g sine theta. Sine theta can be approximated by x divided by L. And substituting that into sine theta, you will be able to establish a relationship that acceleration is equal to minus g divided by L multiplied by the displacement x. And for object that undergo simple harmonic motion, A is equal to omega square x. So from there, we know that omega square is actually equal to g over L. And we could actually derive the expression for the frequency and as well as for the period of the oscillation. Let's take a look at an object that will be undergoing oscillation between two springs. Initially, when the object is at rest, elastic force F1 must be equal to elastic force F2. So from there, we can establish the relationship that K2E2 is equal to K1E1, and E1, E2 are the respective extension of spring 1 and spring 2. Thereafter, we let X be from left to right and let it be the positive convention. So in this case, we'll now shift the object from its equilibrium position towards the right by a displacement X. So studying the force acting on this object now, we will know that your F1 is directed in the direction that is negative. So hence F1 is negative K1 bracket E1 plus X. While your F2 is actually directed in the positive direction. So F2 is K2 bracket E2 minus X. So from there you can work out the expression as such. And we could easily cancel these two out since K2 E2 is equal to K1 E1. So from that, we can then make MA equal to minus K1 K2 multiplied by X. And we can then establish a relationship as such. Once we establish the relationship of A in terms of the displacement, we can then use A equal to minus omega squared X. And in this case, omega squared X is actually equal to this expression. And from there, and again, we can derive the frequency and the period. Let's take a look at the floating cylinder. In this case, initially the cylinder is at rest and the weight is equal to the upthrust. So from there, we can say W is equal to LA rho g. L is actually the length of the cylinder that's submerged under water. A is actually the cross-sectional area of the cylinder, while rho is actually the density of the fluid. Now let us set the convention that downward is positive. And let us decide, let us actually move, let's push the cylinder further down by displacement x. And from there, we know that there are two forces acting on the, we know that there are two forces acting on the cylinder. First is weight, which is positive, and next is the upthrust, which is actually negative. So you can see the weight is mg, the upthrust is minus L plus X times A, because now there's actually a larger volume of water that has been displaced. And we know that mg, the weight, is equal to LA rho g. So actually LA rho g and the mg will cancel away, allowing us to establish a relationship that MA is equal to minus A rho g bracket X. And once we are able to establish this relationship, we know that A is equal to omega square X, and therefore omega square is this expression. And in the same vein, we'll be able to derive the frequency and the period.